interactives. We see full screen. And
hello,
yes,
everyone.
we can hear you very well. So please go ahead. Thank you.
Thank you very much for introduction. I will present a quick recap of use of artificial intelligence and machine learning in particle therapy. I will try to be efficient, that also we will have a bigger pause for the lunch. Yeah. So first few words I would like to discuss, actually present about the COSILab, what we are doing. Probably a lot of you're familiar with COSILab, but in any case, just to present. So how we started? We started by doing the control systems for all these big physics projects, for synchrotrons, light sources, and so on. And then basically once particle therapy started to enter, to be widely spread, then basically we were invited by some big vendors to do a control systems for their accelerators. Yeah. And then since then, particle therapy basically becomes, maybe I would say, even the main pillar of our company. So we are doing the services and products for different areas of expertise, doing the hardware and software. And as I said, starting by actually integration of all these different devices. For instance, if you have like a fair project, you have thousands and thousands of devices, and you need basically to integrate them into a meaningful unit or meaningful whole, so that it will work as desired. It can be used for this research and useful by actually researchers. So the idea of COSILab is basically we do the dirty work, so the making the software controls and all the stuff, that you guys, researchers, can focus really on the research and basically pushing the limits of the science. Customers are really worldwide, basically all the biggest labs. There is our software working inside, and we are also a global player. How we are doing, we are really recruiting the best talents from Slovenia and abroad, and we know that to do a good software for you guys, we also need to understand the domain. So basically around 1/3 of the company are physicists. So which are some background in particle physics, for instance, and also so they are understanding the domain, but also they're good in coding. We also have a PhDs from different fields. So for the particle therapy is important, not just the particle physics, but it's also important to understand, let's say, the imaging and so on. COSILab is also certified 13485, means that we are eligible manufacturer of medical devices, and basically oral software is developed according to this standard. This is very important because patient and personal safety is in the first place, and basically our software needs, and it is developed according to the strictest standards to ensure the patient and personal safety. I will just quickly also mention some of the, let's say, the showcases for the different fields. One is that we are doing the control system platform called Kodak for the ITER in France. So basically that the entire control system is then developed based on this platform. Also in Atacama, Chile, the control system for the entire array for the biggest, let's say, ground-based radio telescopes. Also here we developed a common framework which is then used in the astronomy community to build the let's say control systems on top of it. We also did actually Slovenia is now also part of CERN, so we also did work in collaboration with the CERN. Actually in 2008 we did a requirements collection project for the Large Hadron Collider. The requirements were also gathered from GSI, ITER, and so on. Regarding particle therapy, one of the let's say, main examples is the Mediocre Facility. And this facility is quite interesting because it actually combines the research and let's say it's a fruit of the CERN, I would say, like now and Mediostron. Here we did the control system of entire synchrotron. So, and also we did the safety part and treatment room integration. Yeah. So gradually we will moving from basically accelerators to also to the clinical parts of the particle therapy, and now we are actually offering the entire software stack for the particle therapy machines. So let's go to see what are the use cases of artificial intelligence and machine learning in particle therapy. If I can divide in two, let's say, different domains. So one domain is basically use of AI for the clinical workflows, basically to have more efficient workflows, to have a better treatment, to reduce the costs, to reduce the burden of the clinical personnel. So this is the ones which are related to this. Another one are related to machine itself, basically to have, let's say, more reliable machines that we can predict when failures can occur, and then basically have actions based on this, basically to do a preventive maintenance. If we look at the workflow, the clinical workflow, how you have several stages which are now done mostly by humans, by clinical experts. They can be the medical doctors, medical physicists, radiotherapists, and so on. And first stage in the cancer treatment is basically diagnostics, based on which you will then decide how to treat the cancer. Yeah. So in this first phase, you gather a lot of different data. You have, I don't know, different medical records which are in form of a text. You have histology images. You have medical images like MRI, CT, and currently the MD, the doctor, he looks all of these data. They make a consili, then debate, and then they prescribe basically the optimal care path. What is the future is basically to have a AI-based power, let's say, algorithm, which will then speed up this process. Next, once we have the prescription, then we say, okay, you need to go, let's say, to radiotherapy. It can be maybe particle therapy, for instance. Maybe concurrently, you will need also to do chemo or maybe surgery. What is actually interesting that in lately, this combined therapy is something which is really the future. Yeah, the combination of all these different types of treatments, like, I don't know, chemo plus radiotherapy or immunotherapy plus radiotherapy, and so on. If we then focus on the radiotherapy, what is typically done, you are doing the simulation CT. So basically, you want to image the patient in the same position as you will treat him in the treatment room. And based on this simulation CT, you basically contour or segment the image to tumor and organs at risk. Yeah, as I will discuss later and show you, it's quite a cumbersome process. Yeah, and once is this done, then basically use the physics simulation, and this physics simulation creates the instructions for the machine, which are then sent to the machine, and basically machine is then controlled based on these instructions, and radiation is delivered to a patient. So all these different steps, there is a potential to incorporate AI and basically to speed up the process and make it more let's say, reliable. One thing which is also important is that in the current market, if you see that all of these different steps or tools which are supporting all of these different steps are provided by different vendors. And then these vendors are typically living in isolated silos. And this prevents the development and growth of AI, basically because also the data cannot be exchanged so easily. So also important step is to have an infrastructure in place and to have really to develop such a data exchange platform. So there are some initiatives where they want to make this interoperability and data exchange, but it's still in the early phase. If you look at the diagnostic and decision support, so we have the structured, non-structured data. So structured data like images, non-structured are the medical records. So what you first need to do is basically to, let's say, non-structured data needs to be structured. For this, you have, I don't know, natural language processing, which goes through the text and then basically categorize them in some categories, classes. On the other hand, images are much more structured. You have a DICOM where you have a lot of attributes and it's categorized. And of course, idea is to speed up the process because it can be really cumbersome, and also maybe even in the future to improve the human performance. What is in the current situation is that I can say that we are not still at the point to have, let's say, the personalized care, because there is a heavy burden on the medical doctors, in this case radiologists, to spend a lot of time and then to always provide the, let's say, the best optimal solution to a patient. In this respect, the AI can do this because, you know, with AI and in the future it can be done, I would say, in order of minutes. And also what is really important, we have developing countries which lack of professionals. And here there is a big potential for AI applications basically to replace or to have like a second opinion to a professional. For instance, you use the AI to make a diagnosis, and then radiologists or oncologists just go there and check the suggestions from the AI application and then accept or not. In the developed countries like in the USA or Western Europe, typically now you have redundancies in professionals. So basically one oncologist is doing peer review of another. However, for developing countries, we know there are lack of clinical professionals. One of the applications which is already trying to do similar thing is called IBM Watson for Oncology, which is being tested in USA, but still the quality of this program is not on the level which we want to have. If we go to the treatment planning, this is very time-consuming process. Yeah, if you have a friends which are, let's say, dosimetrists or oncologists, they will tell you how this is really time-consuming process. It is divided in two steps. First step is basically contouring, where you need to contour organs at risks and tumor. And this is the manual process. So tumors are contoured by medical doctors, while organs at risk are contoured either by dosimetrists or RTTs or whatever. It's less critical, let's say, to be contoured. And it can really, it can last up to several hours, even up to 6 hours. Yeah. And what is here really important is that organs at risk is something which is visible on the CT image. Yeah? And here, there's a reason also why medical doctors are not involved in contouring these structures. But contouring tumors is something which is typically not visible on the images. And here, MD is using his experience to draw contours. What we know from the market, basically, that this first one, AI-based contouring of organs at risk, is something which is, let's say, more or less solved problem. Of course, it's not still working like totally automated, that you can run the AI solution and then you don't do any corrections. But there are several vendors which are providing such solutions, like Mirada Medical, or let's say MIM, where they provide quite decent contours when then there is not a lot of work then to basically fix them or correct them. The problem is with automated contouring of something which is not visible on videos, yeah, to say like this. And this is the open research topic. There are a few laboratories doing this, like in France, in Lyon. And there is an estimation that this will be also solved, but here it requires much bigger data, basically bigger experience from different people. And this is something which we expect that it can be solved probably, let's say, in next 5 years. Yeah. So currently, contouring of tumors in next 5 years will be still done by a medical doctor. Once we have, let's say, tumor and contours of organs at risk, we can go and do dose calculation, so to do a treatment plan. This is also quite extensive process because there are a lot of trials and errors, and to find the optimal, let's say, the angles of gantry angles for radiation and so on. And this also can last really up to 1 day. So basically, to prepare a plan for a patient, in the worst case, when it's a quite complex plan, it could last, let's say, altogether around 1 day. And what is also in our research direction is to do AI-based dose calculations. So basically, based on AI, you calculate the target dose you want to achieve, and then you use you will use the physics simulation to basically mimic this target dose distribution you want to do. And the story here is not over, yeah. And funny thing is that people, and basically tissue is a living thing, yeah, and they interact with the radiation, and they basically change due to irradiation. And what happens in some anatomical regions is that over the course of treatment, so you typically have like from 20 to 30 fractions, the patient anatomy changes, and then the treatment plan which you did at the beginning, it's not valid, or it's not optimal anymore. And in this case, you will need to do a replanning. And basically, if you want to do a replanning, you need to repeat all of this time-consuming process, which we know that it's cumbersome. And this basically leads to that replanning is done only for, let's say, critical cases, yeah, where this is really, really necessary. And know that it's not done for all applicable cases. In case, once we have AI for let's say, everything, we will be able then to do replanning also, let's say, for the bigger pool of patients, and at the end have better care and better dose delivery. If we go to the preventive maintenance, so COSLab, we were working with basically almost all players in the particle therapy market. And we know that particle therapy is quite costly, yeah? And such stuff as, let's say, use of AI for preventive maintenance is something which can lead that particle therapy at the end is, let's say, cheaper, yeah? But what we see from the industry is that this is still not yet introduced and used by the biggest vendors. Yeah? What we can see that there are a lot of data generated by particle therapy machines. There are a lot of let's say signals which can be monitored, data acquisition, archiving. There are a lot of data that can be processed. There are a lot of space to do a feature extraction, to do analysis, and so on. So there are really a big opportunity here for AI. So the bigger data we have, large amount of data we have, actually it's a more suitable application for AI. Yeah? And we also know that these machines are complex, so it's very hard to model and predict their behavior because it's very difficult in, let's say, an analytical way of thinking to make all of these different root and consequence analysis. What is a good thing is that AI can bring actually benefits. So it can, as I said, decrease the maintenance and service expenses. So you can really optimize. Also maybe on site have just critical parts, not all of them, know in advance when to buy a critical part, send then the team there, because currently you have a constantly present on-site team for each particle therapy system, which is really costly. Yeah. With such application, you can maybe have a team which is then mobile. Yeah. And then the costs are shared among different customers. Of course, you can increase the uptime because you can do a better planning. And at the end, your customers will be more satisfied because your machine is more reliable. What we know that such or similar applications are already implemented in other industries like aerospace, energy, chemical. And there are already well understood set of analytical tools. I think here also in the CERN you did the similar things about the preventive maintenance of CERN machines. So here is something which really, I would say, it's on the door to get industrialized and be widely used also by big vendors. So what is the mission of COSILab is our new initiative called Oncology One, where we really want, based on all these discussions about AI, to improve the clinical benefits, to reduce the costs of the cancer treatment, to make the particle therapy available to everyone, and to have, let's say, one unified solution for entire radiotherapy. So the problem is, as I said, there are silos provided by different vendors, not integrated, and this is something which we would like to change. If I can summarize, artificial intelligence is not yet proven in radio and particle therapy. So there are the first initiatives like this for the contouring of organs at risk, but still this is the, let's say, the early stage of AI introduction. However, this is the future. Yeah, future is really to have a, let's say, human assistant, AI-based human assistant, to have automated processes, to have optimal patient care. So basically that AI on one hand reduce the time of manual processes and having the medical experts, so the MDs, more time to focus on the patient. Also to be widely spread so that you can have a higher patient throughput, so that more patients can be treated. And let's say at the end to have less costly treatments, which is definitely something which is important, let's say, for the particle therapy. So with this, I concluded. I made a really brief overview, and maybe we can have a more time then to, let's say, discuss, and that I can answer your questions. So
thank you very much for this very instructive presentation, a glance to the future, what is going to come, and I'm sure this gives also some job perspectives to participants. So if you stop sharing, we will post the questions.
Yes, great, thank you. So thank you for the question. So the first one, so it is, I think, at least in my lifetime, so, and I plan to live at least, I don't know, 50 years more, yeah? We will not have AI that completely replaces the let's say, the doctor or the physicist. So the idea is that AI creates a treatment plan, but then, of course, medical physicists and medical doctor review this plan and correct if necessary. So also maybe in 50 years, there will be perfect AI treatment plans, but at the end, I think still the medical personnel will confirm or approve this, what is created by AI. What kind of dose calculation do you do takes up today? Yeah. So what is now the trend in the dose calculation is, so the traditional way of treatment planning was to use the analytical models like CCC, collapsed cone convolution. But now what we know, especially in particle therapy, the Monte Carlo is something which is the state of the art for the dose calculation. And Monte Carlo is computationally extensive method. And this is the reason why it can really takes too long. Recently, there are also some treatment planning systems which are using GPU-based implementations, and they reduce the time, but let's say bulk of TPSs, they don't have this ability, and there's the reason the optimization is quite a long process. What kind of algorithm are you using for prediction, classification, or regression, supervised or unsupervised? So this is, let's say, for the diagnosis, yeah. There are a lot of data, and how I was talking with IBM guys, there you would need basically to use an unsupervised, because you cannot have, let's say, enough time to mark all of this and label all of this. For, let's say, treatment planning, there you use the supervised learning. Also, for the, let's say, contouring, it's for organ-centric contouring, the state of the art is to use the deep neural networks, yeah, convolutional neural networks. For let's say, for the dose, the AI dose planning, it is regression. But this is just implementation by some companies, yeah. The most mature thing is basically contouring, and there it's known that if you want to do contouring, you use the convolutional neural network, and actually WNet is something which is standard now for the contouring. How do you overcome problems regarding patient data privacy in order to obtain data sets? Yeah, so this is a very good question. Basically, this is something which we agree with the hospital that they're doing anonymization. Luckily, let's say, regarding the images, the PACs themselves, they have option to export the images in anonymized fashion, which is a good thing. Yeah, yeah. How medical doctors could actually contour the tumor if they don't see it? Yeah. So for the contouring, you also use the fusion of different modalities like PET and MRI. That's true, but still, you at the end contour on CT, and also with fused images, it can happen that some structures are, let's say, the problem is that you need to know where the tumor cells are, and this is may not be visible also on PET, yeah. And that's the reason then once where the doctor then say, based on my experience, even though I don't see, I know that typically tumor is concentrating around this and these vessels, for instance, yeah. And then they also contour this part of the body and say, here I want to deliver the let's say the tumor dose as well. Quality control of non-structured data, different doctor, different diagnostic standards. Yes, I can say here it's a very valid question, and also the additional problem I can even say is that different institutions, they want to do their stuff in a different way, so they have different protocols even, yeah. So maybe for the future, maybe the future will not be in the standardized treatments, but maybe in tools that can be adjusted by local institutions. So if you look at the developed countries like USA, you have like a Mayo Clinic. They say we have, you know, our way of doing stuff is the best in the world, and we will not change it for anything. Yeah? And then you have a MGH, which is also the big thing. They also say ours is the best. Yeah. So the future is maybe not to unify them, but offer them flexibility that they can use AI for their, let's say, in their own way. What language do you suggest for machine learning? Yeah. So in COSLab, we use the standard thing, yeah, Python, the TensorFlow thing. This is okay. Also from the, let's say, medical device regulations, it's okay to use Python. It's easy, it's the passes to the prototyping. So in this respect, we are using this one. Then everybody has to train their own network. So here is idea that you provide the, let's say, default models, which can be then upgraded by the local institution. So of course, local institution can use these default models, but they have ability to train them even furthermore. Yeah. I have a pool of data with a lot of features in from which how to extract the relevant features for the prediction of output of a parameter. Yeah. Yeah. So let's say regarding this question is something. Nice thing about AI is also that in a sense of this, let's say, convolutional neural network is that with a good and a lot of data, let's say, if you have a lot of data, it can also filter out what is relevant and what is not. Yeah. On contrary, let's say, to regression types, when you have, let's say, logistic regression or something like this, there it's quite important that input features are nicely selected, do not correlate between themselves, and so on. With, let's say, deep learning, this is something which is not so critical, let's say. I think I answer. Okay.
Maybe you can unmute yourself. And,
yes, maybe it's quicker.
If you can unmute yourself, you can ask the question online.
To interpret. So here, probably it's about diagnostics, not about contouring. I would assume. Yeah. I can say that let's say the diagnostic is something which we are not doing in COSLab, but I would assume here, I don't know, you will need to have a classification, so I don't know, some random forest or something like this you will need to use, but it's really not images. I meant those information from TPS. So here, what I know how it is done, it's you have different, let's say, those distributions you want to achieve, yeah, and basically You still have a physics, so you still need to use a CCC or Monte Carlo. But what is easier, you have already target the fluency you want to achieve, and basically you just do the optimization of physical parameters of the machine. That then this, let's say, dose distribution is achieved. In this respect, you speed up the process. Still, you will not use AI to really generate an entire plan without any physics. This is something which is still not under research, and I think it's maybe it will be hardly feasible to be done, to be honest.
Okay, great. Thank you very much for the presentation and answering thoroughly all the questions. So many thanks to all the speakers of the morning session, and let us have a lunch break, a short one today. Our apologies for the very dense program that could be actually a full week school, but we thought it is useful for participants to get an overview. So see you at 1:15